Hello everyone, welcome back. In today's lecture, we essentially are going to look at the second criteria that we use for figuring out whether a ductile material will yield or not. So in the last lecture, we looked at the Tresca criteria or the maximum shear stress criteria. In this one, we are going to look at what is called as the von Mises criterion. It is a little bit different from the Tresca criteria, and we will look at how these two criterions are different. Okay? So essentially, by the end of this lecture, what you will be able to do is calculate the safety factor for ductile materials based on the von Mises criterion, and you'll be able to understand the difference between the Tresca and von Mises criterion for yielding. And again, these criteria are yield criteria for ductile materials. These don't apply to brittle materials. Okay, so let's think about what is the von Mises criteria for yielding. Okay, again, as I told you, it is applied for the yielding of ductile materials. Okay, and one of the things that you must keep in mind is that ductile materials have similar yield strengths in both tension and compression. Okay, so what does this von Mises criterion actually say? This von Mises criterion is also called as the maximum distortion energy theory. Okay, it's another name for the von Mises criterion because essentially this criterion is derived from calculating what is called as the distortion energy of the material. We won't have a chance to actually go through what this is, but we will go through at least what the criterion essentially says. So this von Mises criterion essentially states that a ductile material will yield, that is, it will undergo plastic deformation when the von Mises stress or the octahedral shear stress reaches a critical value. So what is this von Mises stress? Okay, we will look at that in the next slide. But before that, I kind of want to remind you that we learnt about this octahedral planes and the octahedral shear stress and the normal stress on the octahedral planes a few lectures back. So we will be using that particular measure of stress to figure out whether a ductile material is going to yield or not. Okay, so what is this von Mises stress? Sigma von Mises, okay, is essentially defined as this term here. Okay, in this case, I have written the von Mises stress as a function of the principal stresses at the point. So sigma 1, sigma 2, and sigma 3 are the principal stresses at any point. And the von Mises stress, the von Mises criteria essentially says that if this quantity that I have circled down here is less than your Sy, which is your yield stress under tension, then the material will not yield. Okay, again, how do you get this Sy? This is the yield strength in tension that you obtain from a uniaxial tension test. So again, if you take the corresponding lab for this class, the first experiment that you'll be doing is essentially a uniaxial tension test from which you'll get the stress strain curve for different materials. And in that class, or in that particular lab, you will learn to figure out what is the yield strength of different materials under tension. So that yield strength is a material property that you measure experimentally. Okay? And the von Mises criterion essentially says that if this particular term that is here is below Sy, then the material will not yield. Okay? So if you look at this particular term, then you essentially have the three principal stresses, sigma 1, sigma 2, sigma 3. And essentially, each one of these terms is essentially the difference between any two principal stresses raised to the power 2. And then you have a factor of 1 over 2 in front of the whole expression. And of course, this entire expression is under the square root. Okay. Now, if you recall the expression for the octahedral shear stress, which is here, it actually has a formula that is actually very, very similar. So if you look at the shear stress, octahedral shear stress formula, it is essentially the same term under the square root, but instead of a 1 over square root of 2 in front of it, you essentially have a 1 over 3 factor in front of it. So essentially, if you look at the von Mises stress here and the octahedral shear stress here, essentially they are related by this particular relationship. So sigma von Mises is 3 over square root of 2 times tau octahedral. So another way of defining the Tresca criteria is that the tau octahedral should be less than or equal to square root of 2 divided by 3 times Sy to avoid yielding. So essentially, this criteria here And this criteria over here is essentially the same. Okay, so essentially you can either write the von Mises criteria in terms of the von Mises stress or in terms of the octahedral shear stress. Okay, now this von Mises criterion can also be represented graphically just as the way we did it for the Tresca criterion. Okay, so again, in this case, we are going to simplify matters and say that it is going to be a 2D stress state. So essentially, the third principal stress is 0. Okay, now if you assume that the third principal stress is 0, then the formula for the octahedral shear stress becomes a little bit simpler. It essentially reduces to something like this, because only sigma 1 and sigma 2 are non-zero. Okay. Now, if you look at this formula here, then the formula essentially contains only sigma 1, sigma 2, and no sigma 3. Okay. And you also have a factor of root 2 over 3 outside the square root. Okay. And if you go back, essentially the criteria for yielding is that tau octahedral should be less than or equal to square root of 2 divided by 3 times S5. So if you use that particular formula, then essentially we end up with this equation. So square root of 2 divided by 3 times square root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 should be equal to square root of 2 divided by 3 times S5 for yielding. Okay. So if this quantity here is less than square root of 2 or divided by 3 times Sy, then the material will not yield. So you can essentially cancel off the square root of 2 over 3 on both sides. And if you do that, essentially you end up with an equation like this. Okay. So it's sigma 1 square minus plus sigma 2 square minus sigma 1 sigma 2 equal to Sy square. Okay. Now you can take the Sy square to the left hand side. And if you do that, you end up with this equation. Okay. And this equation is essentially an equation of an ellipse. Okay. It is not an equation of an ellipse where the major axis are the x and y axis, but it is essentially an inclined ellipse. Okay. So if you plot this particular expression as a function of sigma 1 and sigma 2, right, that is how the yield surface or the yield curve will look like. Okay, so essentially I have labeled 4 points here. So one is the point where sigma 1 is equal to Sy and sigma 2 equal to 0. This is sigma 2 equal to Sy and sigma 1 is equal to 0. And in this case, sigma 1 is minus Sy and sigma 2 is 0. And in this case, sigma 1 is 0 and sigma 2 is minus Sy. Okay, so essentially, if the stress state at any point is such that the sigma 1 and sigma 2 essentially fall within this ellipse. So any point in that ellipse, then that particular point is not going to yield. Okay, based on the von Mises criterion. Okay. Now, in this case, we have looked at a 2D stress state, but you can also expand or extend this particular analysis through 3D stress state. The only thing is that if you take the 3D stress state into account, you also have to take into account sigma 3, which is the third principal stress. Okay, the shape will not be so simple because it's in 3 dimension, but essentially the procedure is exactly the same. Okay. Now, if you recall, the graphical representation of the yield curve or the yield surface in the case of Tresca criteria, the yield curve was something like a hexagon. It was not a perfect hexagon, but it essentially was like an hexagon. In this case, though, for the von Mises criterion, it is actually an ellipse. Okay, so how does the von Mises criterion compare with the Tresca criterion? Okay, so in that case, it is actually very helpful to plot both these things on a single graph. Okay, that is what I have done here. Okay, so here I have plotted both the von Mises criterion and the Tresca criterion, and I have labeled some important points on the curves. The first thing that you notice is that the Tresca criterion or the yield surface based on the Tresca criterion is completely inside the ellipse, which is the yield surface of the von Mises criterion. Okay, so what does it actually mean for the yield surface of Tresca to be inside the von Mises? It essentially means that the Tresca criterion is more conservative than the von Mises criterion. Okay, what do I mean by more conservative? So think of a point here. if you have a stress state that corresponds to a point like this, both these criteria essentially tell you that that particular point is not going to yield. Okay? So any point that is within the hexagon or hexagon-like structure is not going to yield. But if you think of a point somewhere here, okay, that is outside the hexagon but inside the ellipse, then the two criteria actually say different things. The Tresca criteria essentially says that that particular point is going to yield. The von Mises criterion says that that particular point is not going to yield. Okay? So Tresca, in some sense, takes a more conservative approach. It says that even in some marginal cases that something is going to yield, whereas the von Mises criteria says that it is not going to yield. So that is the reason why we call the Tresca criteria to be more conservative. And if you look at this figure, there are some points where the difference between the Tresca criterion and the von Mises criterion is a lot. So essentially, if you think of a point somewhere here, okay, let me just erase that. So if you think of a point somewhere here, okay, essentially if you draw a 45-degree line, then when you hit this point, that is a point Tresca criteria says that the material is going to yield. But the von Mises criteria says that you can have quite a bit more stress, okay, and still not yield, and you will yield only when you reach this point. Okay? So these 45-degree lines, okay, are essentially the states of stress where the predictions of the Tresca criteria and the von Mises criteria differ the most. Okay? And what is special about these lines? These lines are essentially lines where sigma 1 is equal to minus sigma 2. Okay? So it is not just this line, it is also, for example, a line like this. Okay? On the other side, that is also a case where sigma 1 is equal to minus sigma 2. Okay? So essentially for these stress states, that is where the difference between the von Mises criteria and the Tresca criteria is maximum. Okay? And why are these cases, or why are these stress states somewhat unique? These stress states are unique because they correspond to what is called as pure shear. Okay? So what do I mean by pure shear? So if you think of a case where sigma 1 is equal to minus sigma 2, let's think of drawing the stress cube for that particular case. Okay? So in this case, you have a sigma, okay, that is a tensile stress. The other sigma is going to be a compressive stress, but of the same magnitude. Okay? This is equal to sigma 1 and that is equal to sigma 2. Again, remember, we are constructing this square in the principal coordinate. So essentially there are going to be no shear stresses. Okay? But when you have a stress state like this, where you have two principal stresses only, and one of the principal stresses is the exact opposite of the other principal stress, then what you can do is you can take this stress state and transform it to a stress state that looks like this. Okay? Where you have only shear stresses. Okay, so essentially the stress state at this point that is represented by this left figure is equivalent to the right figure, except that now this angle is going to be 45 degrees. So essentially if you take this particular square here and then you rotate it by 45 degrees, you will essentially get this state. And now in this particular state on the right, you have only shear stresses. The normal stresses on all the four planes is actually equal to 0. Okay? So it is only for these stress states that you have a maximum difference between the von Mises criteria and the Tresca criteria. Okay? Now, you have these two criteria. Both of them are for yielding of ductile materials. Which one are you going to use? Okay? And the reason and the answer is, for certain cases use the Tresca criteria, and for certain cases use the von Mises criteria. So typically when you are designing something, okay, you use the Tresca criteria because it is more conservative. So if you are trying to design a shaft or design a beam, you would essentially use Tresca criterion to design the beam. Okay. But once you actually designed the beam and actually made it, now you're interested in figuring out whether this particular structure is going to fail in practice or not, then you use the von Mises criteria. And the reason that you use von Mises criteria is because it is more accurate. So if you already have a beam that is, taking some load, and you're worried whether this beam is going to survive or not, whether it's going to yield or not, right? Then you essentially use von Mises criteria to evaluate whether it's going to yield or not. Okay? So essentially, for design, you use Tresca criteria because it is more conservative. For analysis, or figuring out whether something is going to yield or not, whether something is going to fail or not, in those cases, you use the von Mises criteria. Okay? In the following lectures, we will look at examples where we use the two different criteria for evaluating structures and see whether some of these things that we learned today actually applies in practice or not. Okay? With that, I want to conclude the lecture, and I'll see you in the next video. Thank you.